Hello, welcome to this week's HSC. Today in chemistry, we're going to learn about the history of the atom. So, the first really notion of an atom we have comes from Democritus. He was an ancient Greek dude who thought that matter consists of invisible and indestructible particles called atoms in a void. And this is important because this really helps inform our later conceptions that atoms are the basic building block of matter. Later we might find out that that's not true, but this is the groundwork that really we keep for the next few thousand years. Of course, his ideas are not popular at the time. He was part of a larger movement called atomism. You might notice atoms, and his ideas were famously rejected by Aristotle. And so we have quite a large leap in time before we go to what many people consider as the first atomic theory. And this was by John Dalton, who lived from 1766 to 1844. And in 1803, he published his first atomic theory. And essentially in this theory, he stated that elements, he had three postulates. First, he stated that elements consist of indivisible, small billiard ball-like atoms. In other words, they're like solid spheres. You might notice that the indivisible part carried over from Democritus's definition. Next, he claims that all atoms of the same element are identical. And this is where we get the idea for elements. He also recognizes that different elements have different types of atoms. And finally, as you might recall from Democritus' definition, he states that atoms can neither be created or destroyed. Of course, the first and the third postulates are later proven to be wrong, but this is the theory that pretty much modern atomic theory builds on. And then we go to Dmitri Mendeleev. And while he does not directly contribute to an understanding of the atom's physical structure in the same way that Dalton did, in 1869, he does a very important thing. He arranges the distinct elements based on the relationship between chemical properties and their mass. And he creates a periodic table. You might notice that in the background here. So in this way, I won't get into detail on this, but later on we'll have a video where we talk about the periodic table and its trends. But for now, all you need to know is that the periodic table arranges different elements, and it does so by basis of their chemical properties. Later we learn in some other models of the atom that these are because of the valence electrons. In other words, the electrons are the outer shells of these atoms. But for now, all that the physicists and chemists know are the atomic mass and the chemical properties of these elements. And so not many elements have been discovered. Mendeleev lived from 1834 to 1907, and so he didn't have a lot to work with. And so this is the periodic table that he created. You can see that eventually he predicts some elements. And some of these elements, you might notice, fall into the same categories as they do in the modern periodic table, which just goes to show that his classification of the chemical properties, even though he didn't necessarily know about electrons, was, it's just amazing that it is possible. And so, I believe the ones in pink are the ones that he didn't know. For example, he called scandium, gallium, and germanium Eka silicon, and stuff like that. And so I mentioned that Mendeleev and the scientists of his time didn't know about electrons. This changes when J.J. Thomson discovers the electron. He lived from 1856 to 1940, and in 1904, he proposes a new model of the atom after he confirms the existence of electrons. And so he realizes, so the experiment he does to find electrons is that there's a beam called the cathode ray beam, and he notices that it curves whenever an object of charge is placed towards it. It curves away from a negative object, and it curves towards a positive object. So he concludes that the cathode ray is actually made up of these small particles with negative charge called electrons. and these are small, have negative charge, mass is almost negligible, and so he realizes that these electrons must be part of the atom, and they must be what causes their chemical properties. And so the model he comes up to describe this is the plum pudding model. So in this model, there is a sea of positive charge that never changes, and then there are these negatively charged electrons, kind of wafting around, having a jolly good time. He calls this plum pudding because, well, it's kind of like plum pudding. There's plums in a pudding, and the pudding is kind of the positive charge, the plums are the negative charge. So it's an interesting theory, but it does later become disproven by Ernest Rutherford, who lived from 1871 to 1937. I believe this is the guy who actually later discovers radioactivity, but that tangent aside, in 1911, he discovers that the atom is mostly positive at the center, so the plum pudding model can't be correct. And then he also postulates that it's mostly empty space. And so the model he comes up with is that these electrons are kind of bouncing around within the atomic radius, and there's like a centralized positive nucleus. And the way he discovers that the atom is positive at its center is the gold foil experiments. So what he does is that he throws alpha particles at a piece of gold foil, and he has a screen set up around the gold foil to detect where the alpha particles kind of bounce off to. And so if you look towards the right, in Thomson's model, most of the atoms would just most of the alpha particles would just fly straight through. They would just fly straight through, and there wouldn't be many collisions. However, what Rutherford discovers is that a surprising number of them actually bounce back. So in other words, there must be a positive core, because that's the only place that they're bouncing off of. And he does a bunch of experiments, and this is what he finds. And that's super fascinating, which causes him to, create this model of the atom. And then we have Niels Bohr, and only a few years later, from Rutherford's model, it should say improved on Rutherford's model, but he improved on Rutherford's model and proposed that elements move around in the positive nucleus, which Rutherford established, in the shells. And he also said that these electrons, they move up or down these shells by emitting or absorbing energy. This model was presented by Rutherford and Bohr together. And so you can see that, this is basically the model he comes up with. There are different shells of different electron. There are these shells, and they have different levels of electrons. And these electrons can either emit photons to go down levels, or they can absorb photons and go up levels. Obviously, the latter is much harder. And so what Bohr's model does is that it actually paves the way for an explanation of some of the chemical processes that Mendeleev puts in his periodic table. You can see here that atomic radius is a trend that they knew, but Bohr's model actually introduces paves the way for the introduction of stuff like electron affinity and ionization energy. Electron affinity is just electronegativity, which kind of states how greedy an atom is for other electrons. I won't explain it in depth right now, but it does have to do with the number of valence electrons in the outer shell. And Bohr's model was, with these shells, able to fully explain these valence electrons. And then we have James Chadwick. So up until Bohr's model, the nucleus was thought of as just positive, so full of protons or whatever. And this was fine until him and some physicists noticed that the mass of the nucleus was much larger than the amount of protons it should have. In other words, the amount of protons that balanced out the charge of the electrons did not account for the entire mass of the nucleus. And so Chadwick, he formulated the existence of neutrons, which were neutral particles that were held in the nucleus together with protons. And so this is the improvement on the Bohr model he suggested in 1932. Again, not that far off. You can see that these discoveries are from Democritus, gradually becoming in shorter and shorter time lengths. And then, oh, I forgot to mention, Bohr's model and Chadwick's models are the ones more commonly taught in schools, just because they're a lot simpler and shells are a useful way of thinking about it. It's a classic example of teaching kids simple things that they're going to understand before you move on to more complex models and abandoning those entirely. And so here we come on to Schrodinger's model. He proposes a model in which electrons appear in probability clouds or orbitals. And this is our modern understanding of atoms and bonding. This is the stuff you learn in high school, basically. And he does this in 1926, which is even before the discovery of the neutron. And yeah, this is the model that's taught in schools, and hopefully this provides a greater context. But what the orbital model does is that it paves the way for some more advanced chemistry topics. So to the left, you can see the basic understanding of the orbital model, but there's like more specific stuff to the top right, in which there are different spheres of influence. I shouldn't say spheres. Yeah, but yeah, there are different types of orbitals. And then you can see, I guess, trends in the orbitals in the periodic table. You see as the orbitals increase, you can tell that the capacity of the shell is gradually increasing, which is like a part of the periodic table. Yeah. And so, obviously, I'm not going to get into this right now, as with many other things. This is just an introductory video on the history of the atom. But what Schrodinger's model does is the orbital model also allows for the explanation of molecular geometry, which we will soon go over in chemistry. And what this is called is either VSEPR or VSEPR, the VSEPR models. It's spelled VSEPR. And so what it is that it explains the geometry of molecules. So, for example, if you see beryllium chloride, that has a linear geometry. We can tell because it has this many bonding pairs and this many valence electrons, and so it must have this specific angle. And this is all because of the orbitals. And there's some wacky stuff like hybridization and other stuff that goes on with orbitals. But you can see that because of orbitals and the orbital model, we can actually figure out the exact shape of these molecules. And so, finally, this is our most modern understanding of the atom. So up till now, we have postulated that ever since Democritus, we've understood that, well, not ever since Democritus, but ever since ever since Democritus, we've thought of atoms as indivisible, right? And then we discovered the smaller parts of the subatomic particles, like protons, neutrons, electrons. But we still thought those were indivisible as well. And that's where our modern understanding of physics kicks in. Murray Gell-Mann and a few other physicists realized that there's more going on, and this is way beyond the scope of this video, but I just want to make sure that you're familiar with the notion of quantum chromodynamics, which there's a bunch of complex stuff about like color and spin, but all you need to know for now is that it breaks down these subatomic particles into smaller pieces, and it reconciles these with charge, because these subatomic particles should have charge for a reason. And Murray Gell-Mann, he introduces the quark model. Protons and neutrons are both hadrons, and there are different types of quarks, and these contribute to their charge. You can see that the up quark here has positive two-thirds E charge. E is like the amount of charge an electron has, which Robert Millikan discovered in his famous oil drop experiment. But that tangent aside, you can see that 2/3 plus 2/3 minus 1/3 is 1/3. Sorry, is 1, 3/3. And that's the amount of charge a proton has. Now, as for a neutron, you have 2/3 minus 1/3 minus 1/3, which just gives you 0. And so, yeah, this is like the quark model of the atom. We're probably not going to discuss this in depth, more because it's a physics topic and not really a chemistry topic. But I thought it'd be nice to introduce to you quantum chromodynamics, just so you knew about quarks and stuff like that. And so that's all. Thank you for learning about the history of the atom, taking you on this journey from Democritus to quarks. I hope you enjoyed, and if you have any questions, please leave them in the comments. I've been Jason, and again, thank you so much for watching.